Welcome to the online presentation Laser Reseal, combination of accelerometer and gyroscope sensors in a single MEMS chip. My name is Holger Rumpf. I'm with Bosch Automotive Electronics and work in the field of engineering sensor process technology. My co-authors are Jens Frey, Kurt-Ulrich Ritzau, Achim Breitling, Peter Staffeld, and Mawuli Ametowobla, who is with Bosch Corporate Research. Unfortunately, we have no possibility to meet each other in Rotterdam personally due to the corona situation. But, well, since this is an invited talk including Q&A session, there will be the opportunity to ask a few live questions at the end of the video presentation. The outlook of my talk is as follows. First, there will be a brief introduction on MEMS inertial sensors. I will shortly describe the working principle of accelerometers and gyroscopes and present some use cases in the automotive and consumer sector. Then I want to focus on the driving forces, pushing the limits of MEMS sensors, and of course, in the main part of this presentation, I would like to introduce our new laser reseal process, which is an important possibility of pushing the limits of MEMS here at Bosch. I will not just describe the process, but also explain to you how we got there and what kind of challenges we had to overcome. Advantages of the new sensor chip will be presented, as well as further possible use cases in the future. Though most of you are certainly familiar with the idea of MEMS, I would like to spend a few minutes during this introductory talk to give a very brief overview and also to highlight the specific features we have to deal with in MEMS inertial sensor industry. So MEMS is an acronym for Micro Electro Mechanical Systems. The MEMS can be used to act interactively with the environment. Well-known applications of MEMS-based actuators are of course the classic inkjet printheads, but also the very interesting field of new micromirror applications. But the largest market for MEMS is in the field of sensor application, like in the example which I will show you during this presentation. So the MEMS is a mechanical part, as you see on the picture, which is marked with the number 1, and also within the circular magnification picture in the middle. It is produced from a wafer. Second, there's a readout ASIC that is placed next to the MEMS sensor on a lead frame or a PCB board. It is also possible to place it on top of the MEMS. In the case shown in the picture, the electrical connection is achieved by classical wire bonding, connecting the MEMS element with the ASIC as well as the board. Please note that it can be necessary for good performance to integrate a decoupling unit on the board to avoid an influence of external vibrations. Finally, the whole unit is packaged together within a plastic package. Also, metal packages and ceramics are possible. In this way, we have a sensor which is suited to enable and to drive a variety of different applications. For inertial sensors, you have two main types. The acceleration sensor or accelerometer, which basically consists of a movable part, the seismic mass, which is connected to a fixed part, the electrode frame in red. And as you have an external movement, the two parts will move relative to each other, and in between these two comb structures, the finger structures, you will have a capacitive change. What I wanted to mention is that the acceleration sensor is hermetically encapsulated at a pressure of around 100 millibar, which we would call high pressure, and this is required for proper damping of the sensor. A prominent example of application is of course the airbag sensor, which is a typical use case in the automotive sector. So the gyroscope or angular rate sensor is a little bit more complex. You have a so-called drive frame and a Coriolis frame, red and yellow in the picture, and they are constantly oscillating. So as soon as you have an external movement or turning around the axis, then the Coriolis force leads to a deflection of the inner part in blue, the detection frame, which gives you again a capacitive signal and the readout. This sensoring complex is encapsulated in a low pressure, about 1 millibar, which you need for energy efficient oscillations. And one famous example is the ESP sensor, also known as a vehicle stability control sensor. Take a look at the movie how it is working in a car. So this is regular functioning, then there's a obstacle on the road, and which means the car is turning, and this is detected by the sensor. Now it's turning back, and the detection frame is detecting it again. Here you can see a real core of a gyro in operation. The movie was taken by means of stroboscopic illumination. You can see the actuation of the drive frame. The sensor core consists of 3 detection axes which are integrated within one chip and allow the angular rate determination of the X, Y and the Z axis in parallel. More details can be found in the invited talk presentation by Johannes Claassen in the physical sensor session on inertial and resonant devices. In case you have not seen it on Monday, you might be able to watch it as an on-demand video or of course read his paper in the journal proceedings. Let's continue with the actual use case. In the automotive industry, the tiny sensors are used in numerous systems to improve their functionality or even allow them to work. The sensors are used in systems for passive safety like airbag systems and active safety like ESP, the electronic stabilization program. In both systems, the inertial sensors are the crucial part to identify the crash or a critical driving situation. Besides these systems, MEMS are also used in powertrain systems and for a lot of comfort functions. Nowadays, more than 50 MEMS sensors are used in a typical car to improve the mobility in terms of safety, comfort and economy. But MEMS sensors in the automotive were only a starting point. Like in 2006, when introducing smartphones, there have already been first ideas of how to smarten these devices, and Bosch founded these days the Bosch Sensor Tech. And already in 2015, we had about 18 sensors in a modern smartphone. These sensors were accelerometers, gyroscopes, pressure sensors, microphones, magnets, proximity sensors, and a variety of optical sensors as well. And this trend has been continuing till today, where we find about 25 sensors within a modern smartphone. Most of you are probably familiar with all these new functions and features you can find in a modern smartphone, but also wearables and earpads contain more and more features. And this is also possible due to the new software features which can be found in the inertial sensors, which example given contain basic functions for step counting, but also more complicated things like gesture recognition, context and activity recognition. So mobile devices are by far the biggest market for MEMS sensors. And you can see here the figures of the MEMS market forecast, where we look into a sales volume of about 22 billion US dollars in 2023. Also in automotive, its growth is continuing. One of the future automotive trends will be highly automated driving, where localization is based on satellites and sensor data fusion. Especially environmental sensors, just as a camera, the ultrasound sensor, radar and LiDAR systems are used. Now, in order to have a short-term localization, the inertial sensors are the backbone of the highly automated driving. They have to realize, for example, a safe stop. Some colleagues of mine at Bosch did a simulation about the situation of a car driving with 100 km per hour, equipped with an inertial sensor that is using the today's ESP spec, which is already a high performance specification. But after only about 9 seconds, there occurs a lateral deviation of already 4 meters. And this means that the car would be leaving the road. Of course, this is unacceptable, such we have to meet new high performance requirements. So where are we? The whole MEMS story started 25 years ago. First sensors were pressure sensors in motor control units, sorry, but then airbags followed, ESP systems followed, and of course the consumer electronics was getting more and more important. Within the meantime, we have produced more than 10 billion MEMS sensors based on more than 1,000 MEMS patents. When you look at the marketing data, which are published, for example, by Yole, you will find out that Bosch is by far the largest manufacturer of MEMS sensors in the world. So we are very big in MEMS, but we drive an ASIC business as well, and we also look into power MOS. All of these devices are fabricated in Breitling in southern Germany. So we have a front-end wafer fab in Breitling, a 200mm fab, and also we still have a 150mm fab. Breitling is also the core of our semiconductor world, but since 3 years we are now planning and constructing the Dresden site, which will be 300mm fab, where we drive ASICs but also power MOS devices. And the story behind our new location in Dresden is certainly that it is located in a wonderful infrastructure that is already existing in the Dresden area. We have global players, we have small, we have medium-sized enterprises, and we also find high-level, high-ranking research institutes and universities. So the motivation was high to be part of this. We call it Silicon Saxony. And due to the IPSAI program, we were getting even some support from the government on this approach. So much about the introductory part. But what drives the development of our MEMS in general? Mostly, you want to have three things. You want to have a smarter sensor because the reduced footprint enables new applications like wearables or earplugs, or even integration into the clothing. And you want to have a better sensor because higher sensitivity enables new functions. And of course, like always, you want to have a cheaper sensor because it makes the applications more affordable. Of course, this basically holds true for all types of sensors. For MEMS inertial sensors, it, for instance, means that you want to integrate acceleration and yaw rate detection into one sensor, the so-called IMUs for inertial measurement units. You can see this, for example, in the Bosch BMI 160, which has one acceleration chip, one gyro chip, and the ASIC in one package. The ideal thing would be that you have the accelerometer and the gyroscope on the same chip, on the same piece of silicon. So coming from this conventional design to a more advanced design. But if you remember, how would you have the two different pressures on the same wafer? That is the big question. The answer is our newly developed technology, the laser reseal process. But how does it work? You start with a MEMS wafer, and as I said, it contains several thousands of individual chips. And you can see here on the right hand side the combination of the two sensors. And as I mentioned, one needs the higher pressure and one needs the lower pressure, and this is now described. So first, the wafer will be encapsulated within another wafer by classical wafer bonding, and during this encapsulation you have the 100 millibar pressure inside both cavities. Then you will open the contacts with an etching step, and in the same step you will etch a hole into the gyroscope cavity. Then you will place the whole wafer into a vacuum chamber where you evacuate the gyroscope pressure. You set the right pressure and do some thermal annealing, and then with an infrared microsecond laser pulse you can locally melt the silicon around the vent hole, and the molten silicon upon cooling down will seal your vent hole. And it really looks like this. So below you see the sensor, and above there's the cap layer, and in the middle there's the laser reseal. And in the insert it's shown that it's really perfectly seamlessly closed and you get an epitaxial seal of the vent hole. The whole process takes about 1 millisecond. And if you take a closer look, you see that there's a tip, and you might ask, where does it come from? So the reason is that silicon has the same density abnormality as water. So the liquid silicon has a higher density than the solid silicon. And when the melt pool crystallizes, it will push out the tip. This is an example in colored liquid in ice, and you see also the formation of the tip. So how did we get there? Well, we started with this very small chunk of silicon in a small vacuum chamber. The chamber was placed inside a laser chamber in our laser laboratory in Renningen. Because the vent holes are very tiny, we had to use camera systems in order to find the right spot. But we also used a high-speed camera system to analyze the melting and recasting behavior. On the right-hand side, you see a nice little video showing the process. In order to get a better statistic, we modified the stage and used a circular vacuum chamber where it was possible to clamp a whole wafer and also to control the pressure more precisely. Here you can see some pictures of the dedicated tool, including a wafer chuck and the viewport for the laser light. Main challenge during the time of development was to hit the vent hole in a precise manner. It turned out that it was rather important to seal the vent hole precisely in the middle, because otherwise a risk of crack formation, which took us a lot of effort, occurred. During the development, we found a large European equipment manufacturer which built a very specific cluster tool for series production, which is a combination of high-performance laser technology and vacuum technology. And such a machine did not really exist before. And now this machine is capable of sealing huge quantities of inertial sensors every day. With this new machine, we were able to overcome the challenge of crack formation due to a very precise alignment process. And when we take a look into the process chamber, we can see these tiny flashes. And every flash is one chip being sealed. Also, at the end of the movie, you can see our metrology tool, which is based on an infrared detection system and which was only acquired for the laser reseal process development. So what are the advantages of the process? From our point of view, it is the enabler for both efficient and high-performance inertial sensors. On the left-hand side, you see the state-of-the-art encapsulation process, and the pressure inside the gyroscope cavity has a large variation between other wafers and also inside each wafer. And in contrast to the picture in the middle, there's the laser reseal. So you see a dramatic improvement of this pressure variation. And since the pressure is directly linked to the sensor sensitivity, we get also a very homogeneous sensitivity. And the good thing is that you can even flexibly adjust the pressure. So this gives us an additional degree of freedom for the sensor design. Of course, there are other possibilities on the market to realize a one-chip solution. For example, you could use a so-called getter, which means you integrate a porous layer into the gyroscope cavity, which will absorb the gas and set you a low pressure. However, you need a lot of costly deposition and patterning equipment, and also you have some interference with the encapsulation process. And moreover, using getter technology, you could not realize a scenario like this. Just for this conference, I prepared a 200mm wafer with 3 different encapsulated pressures, varying from 0.5 millibar to 1 millibar. Just to show you that we can do it. I varied the size of stripes from the notch region to the anti-notch region, keeping the 0.75 millibar stripe width constant and decreasing the width of the 1 millibar area. At the same time, I increased the width of the 0.5 millibar stripe from notch to anti-notch. On the right hand side, you see the actual data in an electrical wafer map. Within the histogram plots on the right hand side, you can see that the included pressure differs slightly from the desired set point. As pointed out in the previous slide, we are actually measuring the Q factor of a resonator, from which we calculate the included pressure. But of course, the Q factor is also influenced by other parameters like trench inhomogeneity, but there might also be some outgassing of included residuals after the reseal process was finished. So there's room for even improving the actual pressure distribution, but please keep in mind that we were already able to improve the Q factor by roughly about a factor of 3 due to the introduction of the laser reseal process, which enables many new features for the actual inertial sensor generation. But what is this particular pressure split on one single wafer good for? Well, you can accelerate the engineering time for a new sensor core by sealing different cores on the same wafer with different pressures, which helps to reduce the development costs and also to accelerate the engineering process. Because in consumer electronics, time to market is everything. So what can you expect for the future? Laser Reseal is now in production for the new IMU BMI 270. And only for this single product, there will be many million pieces to be produced. And also the next generation following the BMI 270 will contain laser reseal. And the thing is that there are more potential applications in our mind. So basically, every time you want to precisely include a specific vacuum or a low level pressure, you can use the laser reseal. For pressure sensors, for example, or even for other materials like glass, for microfluidics, I think there are many more applications possible. And the great thing is that there are always new applications for sensors. Of course, we also look into other laser process technology combinations with MEMS wafer production, and I'm sure you will see future production where this combination is a key factor. Finally, I would like to thank the German BMWI, the Bundesministerium for Wirtschaft and Energy, in the frame of the important project for common European interest IPCEI, which helped not only driving the Dresden fab, but also various PhD works together with institutes and universities. I thank you for your attention, and as indicated in the beginning, I am happy to talk to you online in the Q&A session. So, hello, let me conclude with a short selfie. As already mentioned, my name is Holger Rumpf, and I'm with Bosch Automotive Electronics here in Breitling, southern Germany. I'm also working as a lecturer at the University of Applied Science, also in Breitling. I'm happy to answer your questions in the Q&A section. So, see you later. Bye.